Alright everyone, we're back now with another demo using Ansible for network automation. In the past I've talked a lot about Ansible used for automation of configuration data, and for a lot of folks out there this could be a bit scary to use any platform for automation, right, to make dynamic configuration changes across a data center, campus, branch, what have you. So in this video, we're going to look at leveraging an open platform like Ansible to assist with automating configuration validation, as well as some automated troubleshooting. So the scenario is pretty straightforward. We have two routers, router 1, router 2, in this Ethernet segment of a network. And so what we can do is, if we were to do show IP OSPF neighbor, we see neighbor state is full, and then it looks like there is a BDR on that segment, which is 10.10.21.20, which just happens to be router 2. Now, if we were to do show IP OSPF neighbor, we also see, using the full states, neighbor 10.10.21.10, that's router 1. You'll notice something a little bit off here, where there's a BDR here, and then nothing, no DR, BDR, druther in the states. So this is done purposefully, and we'll look at this in just a second on what's really going on here, as we troubleshoot this network. So if we dive right in, let's get to a bash prompt. What we're going to do is launch this Ansible playbook, which is going to, assist in troubleshooting OSPF neighbor adjacencies. So this playbook, called OSPF Ops, was pre-created. So what we'll do now is execute this playbook. We'll hit enter here. So what we're doing is going to collect OSPF data, right? So this first task in this play is to get OSPF facts. And this is neighbor IP addresses, MTU information, timers, network types, everything we really need to diagnose a possible OSPF issue. So we saw a lot of data come out here. Let's go back to the top real quick. So we can see here, we started the playbook up here. We see the first name of the play, collecting OSPF data. The first task, we got our facts okay, both router 2 and router 1. And these happen in parallel. So, as the number of devices increase, it's still going to take approximately the same amount of time to connect all the devices, which is pretty great, pretty sweet. So if it's anywhere from 12 to 15 seconds to connect per device, it's actually the same amount of time to connect to 10 or 20 devices as well. So if we look at interface IP addresses used for OSPF peering, here we see for router 1, the IP address on gig 00, router 2, IP address on gig 00. So right away we see, okay, they're in the same subnet. That's definitely a plus. Is OSPF active on interface? Yes. So we validated there's some OSPF config on the interface. Process ID check. What I'm doing here is just validating that at least one process is running on the router. So in a given requirement, if this was a live production network, you could do a query for a particular process ID that should be configured. Excuse me. The next thing here is MTUs. So we see here both MTUs are currently configured for 1600. So we have a match here. Network type. Okay, look at this. This is interesting. So one is configured as broadcast and one as point-to-point. So this makes sense, given what you know about OSPF network types, where broadcast networks have DRs and BDRs, where point-to-point networks do not. And the same goes for timers, which is the next section here. OSPF timers, excuse me, OSPF timers show as 10 seconds for the hello, and dead timer is 40 seconds on router 1, and router 2 has no timers because it is a point-to-point connection. Interface status, if we go back to gig 00 on each router, this is the interface being looked at. Each one is up and up. And display neighbors and state. So here again we can see both are full, and then we see router 1 trying to send hellos out there, trying to form DR and BDR relationships. So what we're going to do here is go to router 2, go back on the interface. I always mistype this. OSPF network broadcast. Right, we'll save that real quick. Give that time to reconverge. Or what we'll do is just do a clear IP OSPF process. Force this. Give that a second. Looks pretty good. And what we're going to do now is come back up, and we will rerun the playbook. So again, the same process all the time, right? First step is always to get the OSPF facts. And as you can see real quick already, as expected, both network types are broadcast now. Timers match. One's the DR, one's the BDR, and we're all good. So the next phase is, well, how do we help diagnose and fix problems automatically? So what we can do is, we could come back to router 1. We know the MTUs are already set to 1600. So what we can do here is just come back here, come to gig 00, set the MTU to 1500. So we're just going to set that for now. Clear the screen. Rerun the playbook another time. Give this a few seconds to run. And as this runs, we can think about what we're expecting to see. And it's pretty straightforward on what we're expecting. But if we just scroll up, we do see 2 MTUs that are mismatched. So we're displaying this data. So in theory, we displayed both MTUs. Somebody could overlook that, even looking at these debug messages. So what we can do is take the next step and take a second to play, add it to the bottom of our playbook to help diagnose the issue. So I'll come back to this playbook in just a second. So we'll come back here. We're going to run this playbook again. So this is a full automated workflow right now, and going through in this playbook. So right now there's 2 plays. The first play is the same play we've been running, which is collecting the data and gathering the facts and displaying the facts about the device through debug messages. The second play that was just added down here does something else. The task, disregard this name, a lot of variables shown in there, but again, we're validating MTUs again down here. We're saying router 1 MTU is 1500, router 2 is 1600. Here we're explicitly stating MTU mismatch. And we're skipping a task called MTU match because they don't match. Self-explanatory there. But this last task, and we could have stopped right here just after displaying MTU mismatch. But I want to take it to the next level, saying, okay, now we have 2 MTUs that are mismatched. One is higher than the other. So in this situation, we're assuming we're going to be deploying some sort of overlay technology over the wide area network, over these routers, right? Or just over this router in a data center, right? This is a theoretical concept that we're talking about. But the new MTU should be 1600. That's set. So what I'm doing here is doing the auto reconfig of MTU by increasing the lower MTU to be equal to the higher MTU value. And this succeeded. This is okay. So if we go back to router 1, we previously made this 1500. If we do show IP interface, gig 00, pipe, include MTU, we see now this automatically changed to the 1600, which is great, right? And if we run the playbook one more time, this would be skipped, and this would show green saying that they match. All right, so this really sums it up from an actual deployment perspective on on how an open platform that can be customized to any enterprise or any customer's requirements, and how it can be done, right? So, and this is the benefit of these newer types of platforms and tools out there that have off-the-shelf modules, from Ansible as an example, and just as easy, custom modules can be built and reused over and over again without diving into actual code. So if we look at the playbook, we'll just take a minute here to review it. But this is the first play up top, and the first play, as we saw a few times already, this is collecting OSPF data from routers. There's two routers in this group, a router 1 and router 2, and we're gathering OSPF facts from each device, and this is the host name of the device taken from the host file, and then in the host file there's also an interface specified which we should focus in on to make sure that it's in the proper state, MTUs and whatnot. So we're specifying the device and interface per router. And what happens when this module is run, there's data that's returned back to via the playbook run. And what I'm doing is storing that data and registering that data in a variable called OSPF data. So as you can see, I highlighted OSPF underscore data, and you can see every other place that we're using OSPF data. So this is a variable, it's a hash or Python dictionary, and the variable that I returned from the playbook is actually called OFacts, or OSPF facts for short. So it's OSPF data dot my dictionary dot the actual variable that we want to pull. So the outgoing interface IP address, outgoing meaning the outgoing OSPF interface. Then we look at, is OSPF active on the interface? Does the process exist? So we see these different iterations here, and these are just things that I've built, in this Ansible facts, in this OSPF facts module. But the user who develops the module could modify this one, or could add more data, as mentioned earlier, in terms of maybe looking for a specific OSPF process versus just making sure at least one is configured. So the first play is really just a matter of gathering facts and then displaying, a bunch of debug messages down here. And the second play, what's going on here is we're defining some variables to use. Root is router 1, so we have to compare data from router 2 against something, and that's going to be router 1 here. And ultimately, if we look at the tasks, what we're doing is, if we go back to the run, we saw this message here, 10.1.1.1.10 MTU equals 1500, and again R2 MTU is 1600. That here is just this statement. So these curly braces just have variable names inside. We're going to display MTU mismatch only when R1 MTU does not equal R2 MTU. And we're going to deploy MTUs match if they do match. Again, straightforward. And the last task down here is executing the automated change that was done to, for example, to bring R1's MTU back up to 1600. So what we're doing is using another custom module called MTU, and we're sending this module a variety of variables, in order to figure out where do you configure the MTU and what settings to actually use. But also we're going to be using this module only when R1 MTU does not equal R2 MTU. So that's the high level of this playbook, and the overall idea to leverage automation platforms in general, right? Doesn't have to be Ansible, but this is just a bit, it's fairly straightforward to get going. But again, just to show the concept of leveraging automation platforms for automated validation and potentially reconfiguration, right? So this is the tip of the iceberg in terms of, we could have automated OSPF network types and hello timers and, dead timers and things like that, right? If they didn't compare or didn't have the same values. So just automating the change of MTU is just to show the example on what can be done. So that's all we have for you. All I have for you today. Using Ansible for network automation and validation. Hope you enjoyed it. Feel free to comment on the blog post associated to this video. All right, talk to you guys soon. Thanks.